Okay, let's look at carbon and hydrogen interacting. So the overlap of those half-filled orbitals worked okay for H2S. Let's see what happens with carbon and hydrogen. So here is the orbital diagram for hydrogen again. Here's the orbital diagram for carbon. If we're thinking about overlap of half-filled atomic orbitals, what are we predicting here? Well, we're predicting that this hydrogen is going to overlap with this half-filled orbital here, and that we're going to have another hydrogen, and that one's going to overlap with this half-filled orbital on the carbon. So here we're just drawing the two half-filled orbitals because this one's empty. There is a p orbital, but it's empty, so we're not going to draw pictures of it. So we've got this orbital, and we've got this orbital half full, and they're going to overlap. Here's the s orbital on the carbon. It's got that pair of electrons. So this predicts that we would have a molecule that is a carbon with two hydrogens, and that the bond angle would be 90 degrees. You see what's happening here? We're taking these individual orbital shapes, and we're bringing the atoms together, and we're having the orbitals overlap with each other, kind of like sticking together. This is not what we observe in reality. In reality, we observe that carbon and hydrogen form a compound that has 4 hydrogens, not 2, and that the angle's not 90 degrees, it's 109.5. It's actually a perfect tetrahedron. So obviously something is missing. Any questions? Well, so far we've been assuming that the orbitals in a molecule are the same as the orbitals in an atom. And that's probably not true. Hybridization is a mathematical procedure in which we take the standard atomic orbitals and we combine them to form hybrid orbitals. So what are orbitals, after all? They're regions of probability. They are wave functions where an electron is likely to be found. You can take those functions and combine them together. It's a little more complicated than averaging, but it's along the same idea. So these hybrid orbitals correspond more closely to the actual distribution of electrons in a molecule. They're still localized on atoms, but they're going to have different shapes and different energies than the s, p, d, and f orbitals that we see in individual atoms. What hybrid orbitals do is they minimize the energy of the molecule by maximizing the overlap. The better the overlap, the lower the energy, the more stable the molecule. So that they're going to give us better overlap because the electron probability density is going to be concentrated on one side, on one lobe, instead of on both sides. Hybridization does require energy. This just doesn't happen by itself. But it's like an investment where you're going to get a return on your investment. The hybridization will happen when the energy stabilization gives us a payback of that energy. What we're going to do to simplify things is we're just going to look at hybridization of the interior atoms. We're going to assume that the terminal atoms are not hybridized, and that'll just make things a little simpler. Atoms that form more bonds are more likely to hybridize than something that just forms a single bond. So, general statements about hybridization before we get to pictures of what's going on here. So, the number of standard orbitals that you're combining together always equals the number of hybrid orbitals that you end up with. If you hybridize 2 orbitals, you end up with 2 hybrid orbitals. If you hybridize 3, you end up with 3 orbitals. So the number of orbitals stays the same. The particular combination is going to determine the shape and the energy. So if you've got an S and a P, you'll get one energy and one shape. If you've got an S and 3 p orbitals that are hybridizing, you're going to get a different energy and a different shape. The hybridization that actually occurs is the one that gives the lowest energy. So calculating which combination of hybrid orbitals gives the lowest energy is a lot of calculations, and it's beyond the scope of the class. So what we're going to do is we're going to use Vesper theory to predict the hybridization. And that's a lot less math than actually doing the calculations. I wouldn't be able to do the calculations. Okay, so here is an orbital diagram for the valence electrons in a carbon atom. And this isn't the little boxes in a row. This is the, we're showing energy increasing here. So carbon has a 2s orbital and 3 2p orbitals, and there are 4 valence electrons. And so we learned that in a carbon atom, the first 2 electrons are going to go here. The next 2 electrons are each going to take their own orbital. So in the quantum hotel model, we've got 2 electrons sleeping head to toe in the one bed in this s orbital. This is the room S on the second floor. This is room P on the second floor, and it has 3 beds. You got 2 electrons coming in there. This guy's going to take his own bed. That guy's going to take his own bed. They're not going to sleep head to toe when they can each have their own bed. That'd be dumb. So that's what the atom does. When we hybridize these, what we say is, well, let's take all 4 of these orbitals. These are not the same energy. This is higher energy, and this is lower energy. Let's hybridize them, kind of average them together. We're now going to end up with 4 identical orbitals. They're not going to be as low in energy as the s, but they're not going to be as high in energy as the p. They're going to be in between. They're all the same now. If they're all the same energy, then those 4 electrons can each have their own orbital. We say these orbitals are degenerate. They have the same energy. Any questions? I remember hearing about this in honors chemistry in high school, SP3, and I can still picture my teacher, Mr. Floyd Sturdivant. He kind of looked like Albert Einstein. He had crazy hair, and he always wore his lab coat unbuttoned, and he walked really fast, and he talked really fast. And I was like, what the heck are you talking about? So if this is the first time you've heard about hybrid orbitals, you're probably feeling that way. The second time I heard about it, in the next chemistry class, I was like, oh, that's what he meant. It's going to take a little bit before this can make sense to you. Yes?
What's the P3 space?
Oh, that's good. I forgot about that. So these now are combinations. They're, over here we had 2s and 2p. These aren't s orbitals, and they're not p orbitals either. They're a combination of 1s and 3p orbitals. We took these 3 p orbitals and 1 s orbital, and we put them all together. So we call these sp3, because it's a combination of an s orbital and 3 p orbitals. Thank you for asking that. So looking at our balloon shapes, what happens when we're doing this? So we've got the s orbital, and we've got p orbitals in the carbon atom. Those are the unhybridized orbitals. So there are 3 p orbitals, and they are at right angles to each other. These orbitals have a lobe on each side of the nucleus. So what we're going to do is we're going to take these wave functions, the equations that describe those shapes, and we're going to put them together. And when we do that, we end up with 4 shapes. They are the same shape, but they're oriented differently in space. And so they're going to be oriented symmetrically, and they're going to form a tetrahedron. What is the little part?
The 3.
Oh, the 3? The 3 means I'm using 3 of the p orbitals, sp3. We don't write S1 because we're chemists, and we don't write the number 1 unless we have to. Right? So it's sp3, meaning an s and 3 p's. So when you combine these, and remember you have positive and negative phases, and so when you combine this with that, you're going to end up with one side getting bigger and one side getting smaller because of the phases in those orbitals. So it's like adding waves. You've got constructive and destructive interference. So you get constructive interference on this side, destructive interference on that side, and that's why one side gets bigger than the other. So we're going to end up with these four shapes that are equivalent in size and energy and shape, but they're oriented differently in space. So they're going to be symmetrically oriented. They're going to make a tetrahedral. So if we show them all together, they're going to look like this. Now, what we do to simplify the drawings, because isn't that already complicated enough, we're going to ignore that little lobe on the other side. It doesn't have much significance in terms of the bonding, and it makes things really complicated to look at, and so we're just going to ignore it, but we understand that it is there. So here we have our four. We get 4 orbitals because we took 4 orbitals and combined them together. We still have 4 orbitals, but they're now sp3 hybrid orbitals. Questions? So to do an orbital diagram for this, we're again showing each orbital as a box, and now all 4 of these boxes are going to be put together because they're all the same energy. So this is like 4 beds in the same room. So it's a little bit like they did some construction on the 2nd floor of the Quantum Hotel. There was an S room with 1 bed, and there was a P room with 3 beds. They were right next to each other. And you had to pay more to stay in the P room. But they did some construction, and they took the wall down between those 2 rooms, made it 1 room with 4 beds in it, and now the price is the same. It's more than the S room, but less than the P room was. And so now we've got 4 beds in there. The 4 electrons that were staying there can now spread out, and they can all have their own beds. Does that make any sense? Again, we have the parallel spins here because of Hund's rule. Now we have 4 orbitals that are half filled, and each of those can overlap with an s orbital from the hydrogen. So let's add in, here's hydrogen, and its orbital diagram is just going to be this 1s. It only has the 1 electron. So these 2 can overlap, and then we can have another hydrogen that's half filled, and that can overlap with this one. Do you get the idea? So each of those 4 purple hybrid orbitals can overlap with a half-filled orbital from a hydrogen. And so we're going to get 4 hydrogens bonding to the carbon. And then the angles here are going to be 109.5, right? Because this is a tetrahedron. This agrees with our experimental observations. Any questions? So imagine these, weird balloon things, right? You've got these orbitals, and they're half filled, and you just bring these 2 atoms, these 2 balloon structures together, and their balloons are going to overlap. Those are wave functions, not solid objects, and so they can overlap with each other. You can also have a lone pair in one of those hybridized orbitals. When you have this lone pair, that's going to reduce the tendency to hybridize, but it can still do this. So for ammonia, let's look at nitrogen here. So if we look at nitrogen by itself, how many valence electrons does it have? 5. So if this is S and this is P, we're going to put 2 electrons in here, and then 3, 4, 5. Right? Those would be the atomic orbitals just on a nitrogen atom. When we hybridize these orbitals, we make them all equal in energy. They're degenerate. We took the S and we took 3 p orbitals and we combined them together, and so we're going to call them sp3 instead of calling them George or something. We still have these 5 electrons. So when we put those in, they're each going to take their own orbital, and then that last guy's going to have to pair up. So here we have a full orbital, and we have 3 half-filled orbitals. So that's the illustration here, the purple. This is the one with the pair in it, and each of these is a hybrid orbital that had 1 electron from the nitrogen, and it's overlapping with the 1s orbital that's half-filled on a hydrogen. And so we get this hybridized orbital here overlapping. We've got that pair of electrons. Does that make any sense? Kind of. We've got this lone pair up here. Valence bond theory explains the change in angle a little bit differently than Vesper theory does. So what we observe is that the bond angle here between the hydrogens is 107 degrees. Perfect tetrahedron would be 109.5. Valence bond theory explains this because it says this angle is going to be a little bit closer to unhybridized p orbitals, which would be 90 degrees, because the hybridization is not complete. It's mostly, but not all the way there, because this pair of electrons there reduces the amount of hybridization. That's one of the finer points. If you missed that, that's okay. Well, let's look at what if we combine an s orbital with only 2 of the p orbitals. So here we have orbitals for an atom, standard atomic orbitals. We've got the s, and there's the 3 p orbitals. What if we just combine s and 2 of the p's and we leave that guy out? So maybe in the hotel, we're not just taking down the wall, we're moving it over. And so these 2 beds got moved into this expanded room, and now that one's off by itself. The price here, the amount of energy here is the same, but these guys are going to be between. So now we have these 3 orbitals. They're called sp2 because it's an s orbital and 2 p orbitals. So if we take an s orbital and 2 of the p orbitals and hybridize those, combine them mathematically, we end up with similar shapes to the sp3 orbitals, but now the orientation is going to be different. We're going to have a trigonal planar situation. So those are the sp2 hybrid orbitals. And again, this smaller node, this stunted side, we don't show that here because this just gets too complicated. So the molecule H2CO has sp2 hybrid orbitals. So what happens is the carbon, which has this orbital diagram, is going to hybridize. It's going to take the s. Let's see if I can draw this better. It's going to take these 3 and hybridize them, and it's going to leave this one unhybridized. So we end up with 3 orbitals that are the same energy, and this p orbital is going to be a little bit higher in energy, but it's pretty close. And so when you fill these up, these guys are going to take their own beds, and then this guy says, well, I could pair up with him, or for just a little bit more, I could have my own bed in the next room. I think I'm going to go for that. It overcomes the cheapness factor. So you can put the 4 electrons out like this. These are the atomic orbitals for hydrogen, oxygen, and carbon. Hydrogen, again, has this half-filled s orbital. Oxygen, we've got 2 half-filled p orbitals. Oxygen here is going to be a terminal atom, and so we're not going to consider it hybridizing, just to make things simpler. Carbon is the central atom, and so we're going to hybridize the carbon like this. When we do this, we see that now carbon can form 4 bonds, and it will form 4 bonds. So what's going to overlap here we've got two of these hydrogens. This is H2CO. So this hydrogen can overlap with one of those. This hydrogen can overlap with one of those. And one of the p orbitals will overlap with the hybrid orbital, and one of oxygen's orbitals will overlap with the unhybridized orbital. Oh my gosh, right? What? Crazy balloon art, right?
Can we get some clowns in here to do that?
That would be good. We could get some clowns in here and actually make these. That'd be fun. Okay. What do we have here? Well, here's our hydrogen atom. The hydrogen has one electron in the 1s orbital. That's our nice little sphere, right? We're okay with that. Here's the other hydrogen with its nice little sphere. Here's the oxygen. Let's just go back here real quick. What was going on with the oxygen? It had a full 2s orbital, it had a full 2p orbital, and it had two half-filled p orbitals. We are going to ignore those lone pairs right now because we don't want to add anything to this, do we? No, we don't. So for the oxygen, here's one of its p orbitals that was half-filled, and here's another one that was half-filled. Now, what's going on with the carbon? Well, carbon hybridized, and it made these three sp2 orbitals, which, remember the shape? They're going to be like that. And then it's got one p orbital that got left untouched. So when we look at this, here are the sp3 hybrid orbitals. They're purple, because blue and red together make purple. Some of these colors aren't coincidences. Those are hybrids because they're a mixture. And then we have the half-filled p orbitals. Question?
The hybrid part, why would you do the sp2 instead of the sp3?
That's an excellent question. Why would you do sp2 instead of sp3? Because when you do the hairy calculations, it's lower in energy this way. Yeah. So how would you know to do that? I'm going to show you that we will look at Vesper theory, and we will see why we would choose sp2 instead of sp3. Yeah. Good question. So when we have overlap here, the carbon has these three purple orbitals, the hybrid ones. My pointer's dead. There it is. So one of those overlaps with the hydrogen. One of them overlaps with another hydrogen. One of them overlaps with one of the p orbitals in the oxygen. And then we've got this p orbital that's half-filled on the carbon and this p orbital that's half-filled on the oxygen, and they're sticking straight up and down. They can't overlap end to end like these are doing. So they do this really weird side-to-side overlap thing. Do you think that overlap is as good as this overlap? No, it isn't. So we have two different kinds of bonds here. This end-to-end overlap is called a sigma bond. And the Greek letter sigma is a lot like an O, right? And if you look from this carbon to the oxygen, what would that bond look like? Those two round balloons overlapping end-to-end. It would look round, right? Sigma's an overlapping end-to-end, and it's symmetrical around the axis. This side-to-side business is a pi bond. And so if you think of it this way, it's the letter pi. I should have done that. I meant to do that with the fat marker. So pi. So that's a pi bond. It's a side-to-side overlap of these p orbitals. So this is a sigma bond. These are also sigma bonds because we have the end of this orbital overlapping with the hydrogen. So this is called a double bond because there's two bonds between the carbon and oxygen. Yeah?
I was going to ask if we were going to have to be able to identify a sigma bond and a pi bond.
Yes, you will have to identify a sigma bond and a pi bond. So this is a double bond. We've got this bond here, and then this and this is one bond. It looks like two, doesn't it? But this is one orbital right here. So this is the p orbital, and this is a p orbital. It had two sides, right? Two lobes, because it's a wave function. It's like a standing wave for the electron. And so what's happening here is this lobe is going to overlap with that lobe in a side-to-side manner, and the other lobe is going to overlap like that. And so we have electron density above and electron density below this bond. It's one bond, though. It's not two.
So that's the pi bond.
That's the pi bond, yeah. It's both sides. And I know that's a little disturbing, but there it is.
How do you pronounce it, the second one?
Sigma.
Oh, sigma.
Yeah, so this is sigma. It's the Greek letter sigma. And this one is pi. Which makes me think of pumpkin pie. It's pie season. Okay, let's talk more about that pi bond. So the pi bond overlaps or results when we have side-to-side overlap. And like I said before, the electrons occupy both lobes. So here is a half-filled p orbital on one atom, a half-filled p orbital on another atom. This electron occupies both sides, both lobes on that atom. But it's not at the nucleus. And we had the example of the string, and it looks like a standing wave. So these two overlap side to side. We have one pair of electrons in this combined thing. That's one bond. The electrons are on both sides. Here is a half-filled p orbital and another half-filled p orbital. Remember, the p orbitals are at right angles to each other. So if this is going up and down, there's an orbital that's going right and left. These two can overlap end to end. That's a sigma bond when they overlap end to end. This is going to be symmetrical along this axis. If you imagine standing on this end and looking straight down the middle, it would look like a big circle, right? Like the end of a sausage or something. Any questions? So here's that same molecule, the same picture. Here's our Lewis structure for that molecule. We need to be able to label these bonds. We label them to describe what kind of bond, whether it's sigma or pi, and what two atoms and what the orbitals are that are overlapping. So this bond, these bonds here, these are sp2 hybrid orbitals. And so it's a sigma bond because it's an end-to-end overlap. On the carbon, we have an sp2 hybridized orbital overlapping with an s orbital on the hydrogen. So there's the element, the orbital involved, a dash, the other element, and the orbital it has. This one here is also a sigma bond because it's end-to-end overlap. On the carbon, we've got one of these purple sp2 orbitals. On the oxygen, we just have a plain old p orbital. And so this is sigma c sp2 op. It's like we've just learned a new code. Awesome, right? This one is a pi bond. It's side-to-side overlap. What do we have overlapping? We've got a p orbital on the carbon and a p orbital on the oxygen. These aren't hybrid orbitals. These are just regular old p orbitals, side-to-side overlap. Any questions? We're going to get practice doing this on the worksheet. So valence bond theory gives us more insight into what's going on in these molecules than the Lewis model does. Valence bond tells us that a double bond between carbon and oxygen is actually two different kinds of bonds. It's not two of the same. In the Lewis, the double bond that we see in the Lewis model is always going to be a sigma and a pi bond in valence bond theory. The pi bonds are weaker generally because it's side-to-side overlap. It's not as efficient as an end-to-end. And so when you break a double bond, what happens is the pi bond gets broken first, and then the sigma bond would get broken. And so you can break one of the bonds without breaking both of them. There's a whole bunch of pretty or scary pictures, depending on your point of view. This is 1,2-dichloroethane. So here this is the Lewis structure for this. And so what we're going to have here is we're going to have sp3 hybridization on the carbon. We're not going to be concerned about why that is right now. I'm just telling you it's sp3 hybridization. And so you're going to have single bond, a sigma bond between the two carbons, and then you've got a single bond between carbon and hydrogen, carbon and hydrogen, carbon and chlorine. So you've got these single bonds. Come on, single bonds. And the other side's the same. This sigma bond in the middle, you can get rotation. Let me show you what that means. So here I have a model, a physical model of that molecule. So the purple balls are the chlorines, the white balls are the hydrogens, and the black ones are the carbons. And in this model, you can see that I can twist one of them, and it can rotate around. And so the chlorines can be opposite each other, or they can be next to each other. You see that? That's rotation around this bond. You can get rotation there because it's an end-to-end overlap. Like if you stick your index fingers together, you can rotate your hand around, right, without breaking the connection. We get free rotation around a single bond. With a double bond, you don't get the rotation.
So what would rotation be useful for?
Well, rotation, when you have a large molecule, that makes it more flexible. It can curl up on itself or it can stretch out. You also, when you have a double bond without the rotation, then you get isomers, where it's the same number of the same kinds of atoms and the same kinds of bonds, but you have two molecules that are not exactly identical. Just like your right hand and your left hand. They're the same, but they're not the same, right? You put on a pair of real gloves, not those fake ones. Real gloves, there's a right glove and a left glove, and if you put them on the wrong hands, the thumb's in the wrong position, right? Because your hands are not identical. They're mirror images of each other. So we can get that sort of a situation happening with when we have double bonds or other sorts of things that can also happen. Here we have a double bond between the carbons. That's going to be a sigma end-to-end bond and a pi bond like this. Because the pi bond is above and below the sigma bond, that's going to restrict the rotation of that molecule. And I can show you that with my little model too. Okay, so here I have a double bond. So the model doesn't give us that reflection of the top and the bottom pi bond and the center sigma bond, but it does give us the same idea of not being able to rotate. I can't rotate because there's two things holding that together. This is like you take your index finger and the next finger, I guess that's your middle finger, and you stick them together like that, so they're touching. Can you rotate your right hand without removing your fingers? No. They're stuck together. There's two of them. You can't rotate it anymore. If there's only one, you can rotate, provided you're coordinated enough to do that while you keep your fingers together. So double bonds cannot rotate. Single bonds can. Any questions? Does that make any sense? Valence bond theory explains why this happens. Lewis theory does not. So these are space-filling models now of those same compounds. With the single bond, we get free rotation, and so this can take many different configurations. With the double bond, there's no rotation, and so you're going to get two distinct forms. you can have these chlorines on the same side of the double bond or on opposite sides of the double bond, and it can't transform from one into the other without breaking the pi bond.
Is there a way to tell if it's a double bond and single bond, or do you have to do that?
That's a good question. So with the space-filling models, can you tell that that's a double bond? Not really, no. That's one of the advantages. Well, I guess that's not. That's what I like about, this is the ball and stick model. You can more clearly see what kinds of bonds you have. But these two are different because you can't rotate there because of that double bond. The pi bond prevents it from rotating. This sort of thing becomes important in organic chemistry. Some of these things are precursors for OChem. Yes?
Would those two molecules behave exactly the same, or would they behave differently?
That's an excellent question. Would these two molecules behave exactly the same? No, they wouldn't. They would have some of the same properties. They'd have the same molar mass. But other properties would be different. Some of the chemical reactions that they undergo are going to be different. Their melting points and boiling points are going to be slightly different because of their different shapes. Yeah. So these are called isomers. And biological systems are extremely sensitive to isomers. So it doesn't have to do with double bonds, but there's another version of types of isomers. It has to do with chirality, right-handed and left-handed molecules. And so like sugars, you can have a right-handed sugar and a left-handed sugar. Your body may metabolize one and not the other. For a lot of medications, there are two different isomers. One isomer works, the other doesn't help you, or might even be bad for you. And so very, very subtle differences have big effects in biological systems. So we've talked about sp3 and sp2. You can also hybridize an S and a P, and so that's called sp. No ones because we don't like ones. So we get two sp hybrid orbitals, and then we have these p orbitals left over, just unchanged. We're starting with 4 orbitals. We always end up with 4 orbitals. 2 sp hybrid orbitals. You take one s and one p. You're going to end up with these 2 orbitals, and they're going to be aligned in opposite directions, linear. And so if you put them together, this is one orbital, that's another orbital. This looks a lot like the p orbital. This was one orbital. But what we're not showing on here is this little lobe. So this is actually 2 separate orbitals, S and a P. Let's draw the Lewis structure for acetylene. This is really kind of silly because it's almost the same as its formula there. Right? How different is that? I just stuck a line here. Acetylene is going to have sp hybrid orbitals instead of sp2 or sp3. So when carbon does that, it's going to make sp hybrid orbitals, and it's going to have these p orbitals left over. And again, these 4 electrons are going to spread out in here because the extra energy required to be in that slightly higher in energy p orbital is worth it to be alone, to have your own bed. So we see that each carbon is making 4 bonds, right? And carbon likes to make 4 bonds. So it's going to make 2 bonds that are utilizing the sp hybrid orbitals, and it's also going to make 2 bonds using the 2p orbitals.
So only 2 got hybridized?
Only 2 got hybridized. And again, I'm going to tell you in a minute how you predict how many get hybridized. For now, that's just a mystery. That almost looks like some sort of a raft or something. So this is our acetylene molecules Lewis structure. So what we've got here On the carbon, we said there were 2 sp hybrid orbitals, and they're going to be one on one side and one on the other. So that's this purple one here and the purple one there. One of those overlaps with the s orbital on the hydrogen. The other one overlaps with one of the hybrid orbitals on the other carbon. And this carbon, its second hybrid orbital overlaps over here with the hydrogen. We have also 2 unhybridized p orbitals, one going straight up and down and one going in and out of the screen on both carbons. And so they can overlap side to side.
Are you going to have to memorize what these are going to look like for the exam?
Are you going to have to memorize what these are going to look like? Not really. On the worksheet, you may have to draw these a little bit. Again, I am not going to grade you on the quality of your artwork. What's more important is, can you visualize what's going on? Can you picture the balloons in your mind? That is a really helpful skill because it can help you understand what's going on here. But yeah, there won't be a lot with pictures and stuff. So
are the pi bonds always going to be the unhybridized p orbitals?
yes, the pi bonds will always be unhybridized p orbitals. They're going to stick out and they're going to overlap side to side. So in this triple bond, we have a pi bond here in the front and the back, and we have a pi bond on the top and the bottom. So there's 1 sigma bond and 2 pi bonds. That makes a triple bond. And a triple bond is always that way, because it's the only way geometrically that you can get these things to overlap with each other. And so here they're naming these bonds. So we have a sigma bond in here, the end-to-end overlap between an sp orbital, hybridized orbital on one carbon, the sp hybridized orbital on the other carbon. This one, front and back, and this one, bottom and top, those are both pi bonds, and those are the overlap of p orbitals on both carbons. And then these bonds are sigma, sp on the carbon, s on the hydrogen. So those are all the possibilities for the s and the p orbitals, but we could also bring in the d orbitals. Good news is we're not going to go into f orbitals at all. Okay. So in the Lewis model, we learned that elements in the third row or larger can have expanded octets, right? And that's when we saw these funny shapes like the octahedron. And we get not just 8 electrons on that central atom, but 10 or 12 or 14. Valence bond theory explains this by saying, well, we're expanding the hybridization to include the d orbitals. The energies of 3d orbitals are similar to 3s and 3p. They're not the same, but they're not very different. And so we can pull the 3d orbitals in there and hybridize with them as well. So here's the unhybridized atomic orbitals, 3s, 3p, and 3d. There's 5d orbitals, 3p orbitals, and 1 s orbital. And we can hybridize different combinations. You're always going to start at the bottom. You're going to take an s, and then you're going to grab as many p orbitals as you need. If you use all of those and you need another one, you're going to go up to the d. So here we're taking sp3 and 1d, and so we call that sp3d. So we get 5 degenerate hybridized orbitals, and then we have these 4 d orbitals that are just left sitting there. When you combine these 5 things, they're going to make this trigonal bipyramid shape that we learned about with Vesper theory. 5 things arranged, spaced out as equally as they can be in 3-dimensional space. We looked at the Lewis structure for arsenic pentafluoride, and we predicted its shape using Vesper theory. We can also look at this using valence bond theory. We're going to have sp3d orbitals, and so there's 5 of them. They arrange as a trigonal bipyramid, and each of them will overlap with the unhybridized p orbital on fluorine. So fluorine has an orbital diagram that would look like this. Those are 1, 2, 3, 4, 5, 6, 7. Fluorine has one half-filled p orbital, and that's the orbital that's going to overlap with the hybridized orbitals on the arsenic. This is why fluorine usually forms one bond. Carbon forms 4 bonds. It has those 4 valence electrons, and it'll hybridize in a way that it uses all 4 of them. You can also pull in a second d orbital, and so then this is sp3d2. It's an S, 3 p's, and 2 d's. We're not trying to make it confusing. I mean, if you can come up with a clearer way of naming these things, I'm interested in hearing it. So now we've got 6 hybrid orbitals. They're degenerate, all the same energy. So they're going to arrange in 3-dimensional space, and they're going to form this octahedron. Each of these hybrid orbitals can do an end-to-end overlap, a sigma overlap with another atom. So sulfur hexafluoride. That half-filled p orbital on fluorine will overlap and form a sigma bond with the sp3d2 orbitals on the sulfur. Yeah?
Can you mix the d orbitals with the s, like leaving out the p? Or
No, you can't. So the question is, could you hybridize just the s and the d and leave the p's out? No, you can't. So, if you think about the quantum hotel, right? On the 3rd floor, there's an S room, a P room, and a D room. They're right next to each other. So you can't remodel and combine the S room and the D room without involving the P room, right? Because what would you do? Make a tunnel over? Or, yeah, it's not going to work, right? You can tear a wall down between S and P, and you could incorporate 2 of the P beds or all 3 of them. But if you want to get into the D room as well and take one of those walls down, you're going to have to include the S and the 3 Ps, and then as many as the Ds as you want.
so you could do p and d.
You can't do P and D either. So my hotel doesn't explain why you can't do that, but you can't. Yeah, those are good questions. Okay, so this addresses one of the questions that we had earlier. How do you know what the hybridization scheme is? How do you know it's sp2 and not sp3? Well, the rigorous method of determining this is you would have to do some calculations and figure out what's going to give you the lowest overall energy. That's just way too much for us. So we're going to go with good enough for Chem 1A, right? We're going to assign a hybridization scheme based on the electron geometry of that interior or central atom. So we're going to use Vesper theory, looking at number of electron groups, and use that to predict the hybridization. It doesn't work 100% of the time, but it works most of the time, and that's going to be good enough for us. And I won't give you anything that's an exception on an exam, and I don't think there would be anything in the homework either. Okay, so what we're going to do is we're going to look at the Lewis structure, look at the number of electron groups. So 2 electron groups, that's going to give us an sp hybridization. 3 will be sp2, 4 is sp3, 5 is sp3d, 6 is sp3d2. So basically it comes down to how many groups do you have? You're going to need that many electrons. Sorry, I'm writing on my fingers. And I'm left-handed, so this is always a challenge. Because it doesn't work if you write it on your right hand. Okay. And if you want to write on your fingers at the beginning of the exam, that's fine. So I look at my Lewis structure and I see how many electron groups do I have. And I say, oh, yeah, I've got 3 electron groups. 1, 2, 3. sp2. If I have 4, 1, 2, 3, 4, sp3. If there's 2, sp. Okay. Now the D's, I'm sorry, I don't have more fingers to put the D's on. But you get the idea, right? You start with S, then you go into the P's, then you go into the D's. The number of electron groups is the number of orbitals that you combine to hybridize. That make sense?
Why does it have to be on your left hand?
Because if I do it on my right hand, then it's backwards. Because we read left to right. This way it's sp3. Yeah. I mean, I could, but it just works better that way. And then all day people are going to say, why do you have letters written on your fingers? Because. Okay, so here's a set of instructions for those of you who like this sort of thing. Write the Lewis structure. Use Vesper theory to look at the number of electron groups. Okay? The number of electron groups is what's going to tell you the hybridization scheme. Then we're going to sketch the molecule, beginning with the interior atom and its orbitals. Then we're going to show the overlap with the terminal atoms. We're going to label all of the bonds, sigma and pi, followed by the types of the orbitals. Okay, so write a hybridization and bonding scheme for xenon tetrafluoride. We have to start with the Lewis structure. So xenon, and we've got 4 fluorines, and we have to get the correct number of electrons in here. We've got 4 fluorines at 7 electrons each, so that's what, 28? And xenon has 8 valence electrons, so that gives us 36. I already have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 32, 34. What do I do with the extra 2 electrons? They go on the xenon. Because xenon's a big boy, he can handle it. He can expand. He's in period 3 or greater. He's actually in period 5. And so he has the d orbitals available to expand into. So we draw the correct Lewis structure. Then we look at the central atom and say, how many electron groups? We have 4 bonds. Each of those is 1 group. And we have 1 lone pair. That's a group. So we have 5 electron groups. Right? So you get your fingers out. 1, 2, 3, 4. Oh, I need this, extra finger. It would be sp3d, right?
Why is it 5 electron groups?
It's 5 electron groups because we have 4 bonds and this lone pair. So this is going to be sp3d. So they're wanting us to draw a picture, right? This may get ugly. It's okay. Yours won't be on YouTube for the entire world to see. Okay, so here's the xenon in the middle. Xenon's going to have 5 things. These are going to arrange just like the balloons did. And so we're going to have 1 going up, and 1 going down, and 1 going off to this side, and then this one's kind of going back, and this one's kind of coming forward. You kind of have to use your imagination here. And then over here I have fluorine, and fluorine's going to use its unhybridized p orbital and overlap. And that's going to happen with most of these. Can you say poor planning? We've got a lone pair here. Where's that lone pair going to go? Is it going to go on an axial or on an equatorial? It's going to go on the equatorial because it's got more space. So this one of these is just got a lone pair. And then we've got a fluorine over here. and then we're supposed to identify what these bonds are. All of these bonds are actually the same kind of a bond. They're sigma. They are sigma bonds, and they are between xenon. What kind of orbital is xenon using? sp3d. They're between an sp3d hybrid orbital on xenon, and fluorine is using an unhybridized p orbital. So if we think about what's going on here, if we look at orbital diagram for xenon, it has 8 valence electrons, right? And they're all going to be paired up like that. But it's going to hybridize. We're choosing this sp3 hybridization, sp3d, because when we looked at the Lewis structure, we saw there were 5 groups. So we know we need to have 5 hybrid orbitals. So 1, 2, 3, 4, 5. Those are the things I need to hybridize. I need to choose 5 boxes starting at the bottom. So that's going to give me 5 degenerate orbitals. And those d orbitals are still there. They're just empty. It's like the hotel rooms. They're still there. They just don't have anybody in them. So in these orbitals here, I've got these 8 electrons, right? 1, 2, 3, 4, 5. One, 2, 3, 4, 5.
You're missing a lone pair on xenon.
You're right, I am. Thank you. Wish you'd said that earlier, but yeah. Dang. I can't count. That screws up everything, doesn't it? Yeah. Because as I'm doing this, I'm realizing, hey, wait a minute, that's not going to work, right? Because I'm going to end up with 2 of those paired up. What we actually have is 6 groups. Okay, 6 groups. So that's sp3d2. We need to include another d orbital. So we'll take another one in there. That one is now part of our hybridization scheme. I'm going to get this guy out of there. One, 2, 3, 4, 5, 6, 7, 8. What the heck is going on? Oh, yeah, I need 2 lone pairs. Oh my goodness. So I have 6 degenerate orbitals, and when I spread the electrons out, I end up with 2 lone pairs. So I have to fix this. So this guy is wonky. So what we actually have here is we do have an octahedron. These lone pairs are going to go opposite of each other. So the other lone pair is going to be opposite from the first one. And then this one is going to overlap with the other fluorine. And so what we've got is sp3d2. Yeah. Because I miscounted my electrons on the Lewis structure, and that messed up everything. let's take a break. Okay, let's write a hybridization and bonding scheme for HCN. What's the first thing we have to do? Lewis structure. So we got to draw a Lewis structure. We've looked at this one before, and drawing Lewis structures is not the focus of this, so I'm just going to do it quickly here. There's our Lewis structure. We're going to look at the central atom and see how many electron groups are there. How many electron groups on the carbon?
4. Electron groups?
Electron groups. 2.
Oh, 2. Oh,
A triple bond is 1. So there's 4 bonds, but there's 2 groups. So 2 electron groups. So the hybridization scheme then is 1, 2. I washed my hands, it came off a little bit. SP. So we've got SP hybridization. So let's look at the hybridization that's happening with carbon. So carbon's unhybridized orbitals. We've got 1, 2, 3, 4. That's P, and this is S, right? When we hybridize SP, we're going to take those 2 orbitals, and we're going to have these SP hybrid orbitals, and then we're going to have left over 2 of the P orbitals. So when we put our electrons in, 1, 2, 3, 4. Yes?
I forgot how you figured out that SP only has 2 orbitals and P still has 2. Can you explain that?
Well, SP hybridized, you understand how I got that? 2 electrons in the electron groups, and then I counted on my fingers, right? SP. So that means I'm going to take the S orbital and 1 of the P orbitals and mash them together. So 2 orbitals here, and then these 2 are left out, so they are unchanged. I'm starting with 4 orbitals, I end up with 4 orbitals. Good question. So there are my half-filled orbitals. I've got 2 SP hybrid orbitals and 2 regular P orbitals. So when I draw what's happening here, I've got the carbon in the middle, and it's going to have an SP hybrid orbital in one direction and an SP hybrid orbital in the other direction. This is going to overlap with the hydrogen. I didn't do that very well. Let's get a little closer. So that's going to overlap with the hydrogen over there, and the nitrogen. Now we kind of have to look at the nitrogen as well. Yeah, there's going to be 2 pi bonds. So if we look at nitrogen, and we're going to assume that nitrogen is not hybridizing. So nitrogen's got 5 valence electrons. 1, 2, 3, 4, 5. So nitrogen has these 3 p orbitals that can be involved here. So this is a p orbital from nitrogen, and that's going to overlap here. So this guy right here is a sigma bond between carbon using an sp hybrid orbital and hydrogen using just a regular old s orbital. This bond, this is going to be obliterated in a minute, but because we have to draw more junk. That bond is also sigma end to end. That's between sp on the carbon and p on the nitrogen. Being able to identify the bond is more important than being able to draw the picture. As long as the picture makes some sense to you, that's good enough. Then, so we've got this one overlapping. Let's just change colors here. So what I've done here is I've got this guy overlapping with one of those. And then I've got my hydrogen with its, that's not very good, with its half-filled. And that's going to overlap with the other one. And I have these p orbitals left, and I've got p orbitals left on the nitrogen. So p orbitals are going to go up and down, back and forth. That one was just really ugly. Let's try that again. This sp hybrid orbital was made with one of the p orbitals, and so that's going to be aligned just like the p orbital was. These other two p orbitals, one up and down, and then one in and out of the plane of the screen. And these are going to overlap side to side. So there's one overlap, and then these are going to overlap. And so both of those are pi bonds, and they're pi bonds between p orbitals on the carbon and p orbitals on the nitrogen. Questions?
So you said we're just saying a pi bond only happens when there's a double or a triple, right?
Right. A pi bond only happens as the second bond in a double bond, or the second and third bonds in a triple bond. The first bond is always a sigma.
So there's never like a double pi bond when it comes to like something like that?
You'll never have just two pi bonds. Mm-mm. Okay, we have one more example. CO2. Okay, so again, we have to start with the Lewis structure. So in today's worksheet, you're going to be just taking the Lewis structure that you drew for worksheet 9 and bringing it into worksheet 10. Of course, that's assuming that you did worksheet 9. So we've got carbon in the middle, and it's going to form double bonds with the oxygens. The oxygens are going to have lone pairs. We've done that one before. How many electron groups on the carbon atom? 2. Very good. 2 electron groups. So we get out our fingers. 1, 2, sp hybridization. So this is sp hybrid orbitals. So for carbon, the unhybridized orbital diagram looks like that. And I'm going to take the s and one of the p orbitals and hybridize that. And then I've got the 2 p orbitals left. So this is sp and this is p. This is p and this is s. And then the electrons can spread out and each have their own orbital. So these are the hybrid, this is hybridized. And then what does oxygen have going on? Well, oxygen being a terminal atom, we're going to assume that it's not going to hybridize. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. Those are my p orbitals and my s orbitals. So each of these oxygen atoms, there's 2 of them, each oxygen atom has 2 p orbitals that can overlap in some combination with the carbon. Okay, so I'm going to put carbon in the middle. And it's going to form sigma bonds with the oxygens. So we've got the sp hybrid orbitals, and that's going to overlap with a p orbital on the oxygen. So we have a pair of electrons there. And here we have oxygen with a p orbital. So those bonds are sigma, overlap of an sp hybrid orbital on carbon and a p orbital on oxygen. So that's one of these guys overlapping with one of those guys. The other oxygen will overlap with this one. And then we've got the p orbitals. So carbon has an up and down p orbital. Oxygen has an up and down p orbital. The other p orbital on this oxygen has a lone pair in it. Since it's not involved in the bonding, we're just going to ignore it because that makes our drawing really cluttered. So these can overlap side to side, right? And that would be a pi bond between a p orbital on carbon and a p orbital on the oxygen. Carbon has another p orbital that's going in and out of the plane of the screen. This oxygen, it's got 3 p orbitals, right? It's got this one that we're using for the sigma bond. It's got one going up and down. We're going to say, well, that one's going to have the lone pair in it, and it's got another one going in and out. And so these are going to overlap in front and behind. And those are also pi on the carbon p and on the oxygen p. Any questions? We'll save this